Hi everyone, we are back. I'm just quitting my kernel. And now we're going to get into some fun things, which is using linear algebra and rotation matrices to rotate stresses and strains. So, if you have if you're trying to find stress on a particular angle or a particular plane or a particular direction, you can do and resolve essentially those forces and use equations from statics to find out what is the stress and strain in the new states. We are not going to do this. We will never do this together. So instead, what we want to do is build up a more kind of fundamental framework using linear algebra approach. But we can use these equations that we derive from statics to kind of show, and one of the beautiful parts about mechanics is we get the same answer even if we solve it different ways. So let's look at this stress matrix. Pretty simple. It is basically a plane stress state. So all of the stresses are contained in one plane, the 1-2 plane specifically. So if I want to find my maximum, sig1 is basically telling me if I want to find the stress state where my normal stresses, these diagonal stresses, are maximized. Basically where I only have normal stresses and I don't have shear stresses here. So I can find that here. We're gonna actually come back to this value. So this is going to be my, let's do a comment. This is my max normal stress, sig1. This is my next value, next stress. This is the value of my maximum shear stress when I'm maximizing my shear. This is the angle to rotate to get to max normal stress here. And these would be my stress values for rotation of 15 degrees counterclockwise. Counterclockwise is negative, or actually, clockwise is negative, counterclockwise would be positive. So this is great, but it's not very tangible or fundamental. So instead, we can rotate our tensors using rotation matrices. So if we're lucky enough to have a plane stress state, we can use this relationship, our rotation matrix, and to find our new stresses, normal, shear, we can use this value. So I can go ahead and calculate this out here. That would be my stress. And I can go ahead and see, okay, I want to solve first for when my shear is maximized. So this third equation here, that takes this, multiplied by this, I want to find out when my third equation, my shear stress, when is it maximized? So that's what I'm taking out the third equation, taking the derivative of this with respect to theta and solving for it for equal to 0. So I do this, and I can pull out any of these values, and when I plug this in, what's my value of my shear stress here? 6.4. What's my value of my maximum shear stress? 6.4 here. Excellent, it matches. What about, and you can kind of see, the different equations that will go out. I could also solve what's the angle that sets my shear stress to 0, i.e. when I'm in my maximum or my principal stress state where I only have normal stresses. So again, I could pull out this value here, 19.39. That's my angle. What was the angle that we set here? 19.39. Excellent. I could then plug in, actually we'll call this theta P here. I could plug this in and I could see what's my new stress state. So look I have no shear stresses effectively. What's my maximum my maximum normal stress? 16.4. Next, 3.596. 16.4, 3.596. We're getting the same answer here. This is the beauty, and then I could also check a rotation of 15 degrees counterclockwise. Note that it's very important here, you have to put degree to make this work. So minus 15, so 12.3, 7. Let's just copy this here. Let's see if we get the same results. 12.3, 7 here, 5.96. We've got it. So you can see we could take this linear algebra approach, we could use rotation matrices that are previously derived in order to solve this problem. Now, this is all for plane stress. How do we work for more general expressions of stress? Well, that's for the next video, and we will get into how to do all those fun rotations in just a second. So thanks, and I'll see you all next time. Bye.